So let's start with a very simple example that is based essentially in our intuition and our common sense. Our intuition and common sense, yours as well, was typically developed for very low velocity things. None of the things you live in everyday life are moving very fast. They are all typically moving very slow. And so let me start with a simple example. I've ridden trains all my life. So here's one train, and this is the track. And this train is, notice how I label the track. I put the distance in here, but I put it in terms of time, so it's easy to get. So for example, if this train is moving, say, at 1 kilometer per second, then in 5 seconds it would do 5 kilometers, right? So station B, for example, would be at 10 kilometers, and this one at 15 kilometers from station A. And notice this is a 1 kilometer per second train, right? This is a very fast train. This train will reach Chicago in 40 seconds. So now you grab your best friend, you give him a watch, you put it in the train, and you tell him, after you pass station A, count 10 seconds with your watch and turn the lights on. Let's see what happens. So you expect the lights to be turned at this point, after 10 seconds. So the train moves. Perfect, and that's my artistic interpretation of light. So the train moves, and you see that the train turns the light at 10 seconds, at 10 kilometers, as you expected, right? That's your common sense, that's your intuition. Now you do the exact same experiment. You just increase the velocity of the train to, say, 3/4 of the velocity of the light. It's harder, but you can do it. So it's essentially moving at this velocity, 225,000 kilometers per second. So again, you put your friend in there, and you tell him the same thing. Turn the lights 10 seconds after you pass station A. So you expect your friend to turn the lights when the train is in here. And see what happens. Oops. And that is where it happens. So then your friend comes off the train, and you ask him, why didn't you turn the light 10 seconds after passing station A? And he would say, yes, I did. If you were able to do this experiment, it would be extremely clear to you that the time that passed for your friend in the train is completely different than the time you get here on the ground watching the whole thing. And this is one of the very important things that we get out of relativity. You see how train moves in the different reference frames. How time changes depending on the reference frame. Now this is a thought experiment that was even thought way before any confirmation or Einstein or anything. This effect was theoretically created, of course, after Einstein, of course, before all of these things. But to understand how this was developed, to understand how the concept of this time moving between reference frames, we need to go back essentially to the times of Galileo. And this is what I call the chapter that's really physics before Einstein. Then we're going to have a problem, and then we're going to have physics after Einstein. So this is the principle of relativity. This principle was not done by Einstein, it was done by Galileo, long before Einstein. And essentially Galileo noticed that the only way you can identify that you're moving is by comparing your position to some other things. Essentially, we notice that when you move, something is moving. So if you have an astronaut, imagine you have this situation, an astronaut, and you get rid of all the reference frames. You get rid of the stars, you get rid of the Earth, you get rid of any reference frames. This is your astronaut. It's now in the middle of space and sees absolutely nothing. This guy, as he is, he can do experiments. He feels weightlessness, and he can perform whatever experiment he wants. And he will get the results out of these experiments. Later on, he pushes his thrusters. He will feel the pressure on the back of his backpack, and while he feels this, he will continually feel that he's being pushed, and at some point he's going to release his thrusters. And at that point, he will feel, again, weightlessness. Again, he will be able to do experiments. He will be able to do the same experiment he did before, and he's going to get the exact same results. Now, for us, from there, we can put a big telescope, we can look at this guy, we see this guy before applying the thrusters, and we see this guy after applying the thrusters. We know he's moving, for all we know, according to our reference frame, he's moving. But yet, he can't tell. The experiments he does before applying the thrusters and the experiment he does after applying his thrusters give the exact same results. So, for all he knows, he cannot differentiate between one and another. And this is essentially the principle of relativity. All the states of uniform motion, this is the motion in which he didn't apply the thrusters, is equivalent for the description of physical phenomena. It doesn't matter how, it doesn't matter with what velocity you are moving. You can be quiet in here, you can be moving with a given velocity. All the different reference frames moving, imagine a lot of different reference frames, and they're all moving with different velocities. No matter which one you choose, if you do experiments, you're going to get the same result. And that's the principle of relativity. It's one of the two most important principles in relativity. Now, there's one distinction in here, which is that this is uniform motion. This means non-accelerated. Because accelerated is when he applied the thrusters, he could feel that threshold. At that point, he was being accelerated. And things are different. And we are going to deal with acceleration in the second part of this talk. So for now, we are dealing with things that just move relative to each other with some velocities. But now, we have a lot of different frames that we can move, and the physics is the same in all of them. We need a way, now, we need a way to essentially transform measurements you guys do in one reference frame versus measure some other people do in another reference frame that's moving relative to the first one. And now, I'm going to try to put just a little tiny bit of equations. You don't need to follow them. Many times I'm going to put a lot of equations in one side. You don't need to follow them. You just need to pay attention to what I'm doing in that side. But this is easy enough. I think everybody can follow. Now, this is me. I have a ruler. I can measure stuff. Right? And to me, the distance to the city is 10 miles away. Now you may live close to the city, say 3 miles away from the city. And these two reference frames, your house and mine, are essentially not moving with respect to each other. So I can tell you that my distance of the city, the distance I measure, the distance you measure of the city, is the distance I measure of the city minus the 7 miles it separates. Right? So the distance you measure is the total distance minus this chunk here. Right? As simple as that. And and notice how we deal with time. This is the way physics was done before Einstein. In time in here, we were saying the time you measure is the time I measure. And that's fine because here, these two are not moving with respect to each other. Now, if this reference frame is moving, for example, with respect to this one, the things are pretty much very similar. Imagine if this is moving at some point, it was back in here, right? So you can say that was time 0. And what was done before Einstein was say, well, instead of now you just replace the 7 miles that you have in here with the velocity times time, because as time progresses, this keeps on moving, so the distance between the two frames keeps on changing, and that's the terminal. But they also say that the velocity that you measure is still the velocity that I measure. They kept on assigning this constraint. They kept on saying the time you have is the time I have. And that, as I showed in the first example, is not true once you go to all Einstein's theory. But this is what we call a Galilean transformation. It's a transformation that allows you to go from one frame to another frame. And now, in general, I use me and you because it's easy to relate to, but typically we use prime coordinates, the coordinates with prime and coordinates that are measured something in another reference frame. So now we have these two things. We have the relativity principle that tells you that all the different frames, the physics in all the different frames is the same, and the results you're going to get are the same. And we have a tool to go from one to another, which is the Galilean transformations I just showed. And in principle, you can test this. And this is easy. If you have any equation that you think you can say this is an equation of a law of physics in my reference frame, you can just do the replacement this. You can replace your equation, of course, we have time, we have position. You can just replace the position you have with this, and the time you have with this, and you're going to have an equation that depends only on the time measured from another reference frame, and the position measures from another reference frame. So essentially, just by doing that replacement in your equation, if when you do this replacement, your equation looks the same, you can say that that law of physics that you have is the same in the other reference frame. I'm gonna go only over one example. I put them in here because later on, if you can get this talk from the web, and if you wanna go through all the equations, you can. So let me just go to this example. What is the velocity? The velocity is the rate of distance change. So it's distance over time. And that's the velocity somebody else measures in a moving reference frame. And the only thing I do, I just replace the x primes with x minus vt and the t primes with t. And at the very end, what you get is that the velocity that you measure in that reference frame is the velocity I measure in my reference frame minus the difference in velocity between the two reference frames. Too complicated. What I'm saying is, I'm in a train moving 50 miles an hour with respect to ground. I throw a ball about 50 miles an hour in the direction in which I'm moving. And of course, the people in the ground will measure the ball to go 100 miles an hour. So that's simply that. And you can follow, that's what we call the transformation of velocities. You can follow all these things to see that the accelerations are the same. Once you see that Newton's law are the same because the accelerations are the same. You can also say that the gravitational force between objects with two masses is the same. That is, I'm here, standing here. We have two planets attracting each other. The force you measure is the force anybody else measures in any other reference frame. But there's one thing, this weird-looking equation, which is really the equation of a wave. Waves are not invariant. If I have a wave in here, and you're passing by very fast, you don't see this wave in the same way I see it if you use Galilean transformations. And that was understood before because it was said, well, what is a wave? A wave, imagine I have a tank of water. And I have the wave on top. It's the bulk movement of the water molecules on top of the water. So there is a reference frame that's special, and it's the reference frame in which I have the water at rest with me. Somebody else will try to describe my thing, they will not be able to use a wave equation if they use the Galilean transformation. If they just replace x prime with x minus vt and t prime with t. So this is an important aspect. Of course, again, you don't have to follow the equations at all. Just the important point is that the wave does not satisfy the Galilean transformations. And this is very important. So this is a summary of the physics before 1900. The physics is independent of the inertial reference frame. All the inertial reference frame are equivalent. It means all of them you can use to determine the laws of physics. The Galilean transformations translate from one frame to another. And the velocities will go up to infinity, because if this law is true, that means if I go 3/4 of the velocity of light in a train, and in the train I send another ball at 3/4 of the velocity of light, according to this, the velocity of light of the ball with respect to ground would be 1.5 times the velocity of light. In principle, you can go all the way to infinity with this theorem. And this is all the physics before Einstein. But then we got a problem. The problem was like, electromagnetic waves, Maxwell wrote the whole theory of electromagnetic waves. In fact, Hertz sent and received radio waves in the 1860s, 90s, but then the radio waves were predicted to move with some velocity. Maxwell said, oh, I know how to measure. I know how the velocity of light should be related to some other things that were already measured. And he was able to put that into the equation to say, the velocity of light should be 300,000 kilometers per second. But then the problem is that Maxwell equations are wave equations, right? These things that we said are not invariant to Galilean transformations. If you have light in here and you use Galilean transformations, you don't see it as a wave in another reference frame. So that's a problem, all right? Because we were saying, according to the principle of relativity, you should be able to see all the things in the same way in all the different reference frames. So we have three options in here. Maxwell equations are wrong, hardly, right? Because this guy predicted the whole thing based on things that were already measured, and he named the velocity of light. The Galilean transformations are wrong. The same transformations that tells you if you throw a ball 50 miles an hour in a train that goes 50 miles an hour with respect to ground, you see the ball at 100. That's wrong. And then the relativity principle is wrong for light. And regarding the last one, this is essentially saying, well, if the relativity principle is wrong, that means there is one preferred reference frame for light. And that's when people brought the idea of an ether, something for which light propagates to, something that supports the propagation of light. In the same way that water, for example, supports the propagation of a wave on top of it. So, of course, you can stop at any point and ask questions and interpret it in here. So let me give you an example how they actually determined that there was no ether. Imagine you have just a canal with some flow. If you are at this point and you swim with the same velocity back and forth, 20 meters, the time it takes you is slightly different than the time it takes you to swim transversally, 20 meters. And actually the difference in time is related to the flow. You can imagine if you have no flow, it's exactly the same to swim in this direction or in that direction. But if there is a flow, there's a time difference. And you can actually measure the flow velocity based on that time difference. And Michelson and Morley, they realized of this. And they concocted some sort of a nice experiment. And this is what they thought. They thought, well, imagine there is an ether. Imagine there is something moving through the universe that supports the propagation of light. And you have the sun in here and you have the earth. And the earth is in here fall and it's spring in here. And then you can imagine that the light would move faster when it goes in this way than when it goes in that way, against the flow, right? And you also can imagine that the light will go different if it goes back and forth than if it goes in this direction. Same as the example I gave before. So this is what they did. They use essentially a laser in here, and this is a semi-silver mirror. And what they do at the very end is measure the time difference between the light going in this direction back and forth and coming here, or the light going in this direction back and forth and coming here. And if there's a time difference between the two, you would see that in the light detector because it's some sort of interference pattern. And if you see no pattern at all, that means the distance between the two are the same. If you see a pattern, it means that the time it takes for the light to go back and forth in one direction or in the other is different. And therefore you're saying, so that means there's some sort of a flow going through this direction. And of course you can rotate this instrument, right? If you see nothing here, you can rotate it like that and like that. But Michelson and Morley did not find any variation of the velocity of light in any direction or in any day of the year. It doesn't matter. In this theory, he was measuring there, he was measuring there, in all the places. And also, during the same day, they would rotate the experiment. And they would always get the same result. The velocity of light was the same, regardless of everything. So this is one of the key experiments that show that if there is an ether, we don't really see in a variation of the velocity of light. Also, but at that time they could measure the Earth, the movement of the planets very, very well. And if there was something in here permeating the universe, you would see the energy of the Earth going around the sun, going slower and slower every time. And you would see the Earth losing energy. You would see all planets losing energy. They didn't see that. So that was it for pretty much for the theory of the Earth. And that's the question if you care about it. So what's the solution to this? The problem is simply that light is a wave, and waves are not typically invariant to Galilean transformation. And the solution, of course, was very high. So these are the three options we have. That the Maxwell equations were wrong, that the Galilean transformations were wrong, and that the relativity principle is wrong. Einstein looked at these three and he said, number one, the principle of relativity is valid. That means it's not wrong. That means it's symmetrically nice. Only an ether could violate it, but the ether is not being found. So he said, this is too symmetric, it has to be right. And the other thing he said was the velocity of light in vacuum is the same in all reference frames. And that's essentially saying that the Maxwell equations are right. So the only option we got is that the Galilean transformations are wrong. These transformations I showed you at the very beginning, in which I derived this x equals x minus vt and t prime equals t. Those are wrong. These are Einstein's postulates, and we can verify them. For example, so far we have not seen any law that is different in different reference frames. Nothing guarantees that tomorrow we will not find one that is. But as of now, we have not seen anything like that. And the constancy of the velocity of light in any frame is verified pretty much every day. For example, in double stars. Double stars are just two stars rotate, a system of two stars rotating around each other, like this. And, imagine the Earth is down here below, and we are looking at this thing. And this star over here emits light in all directions. Right? In particularly, when it's there, it's emitting light also in the direction downstream. And when it's here, it's also emitting light in this direction. Now the question is the light velocity, when this star is over here, the velocity of light minus the velocity of the star? And in the same way, and this is in analogy when you grab a ball and you throw the ball and you're moving, we see from the ground the ball moving faster. So is this the velocity of light here and here? We can measure that. We can measure the velocity of this light, and it's not. It's the same. And this is one thing. Another way of doing this is with pion decays. Pions are particles that decay to two photons. If you keep them at rest, you will see two photons going in opposite directions. But we can have these guys accelerate. We can accelerate these guys and have them at a very high velocity, 99% the velocity of light. So then the question is, at some point, one of these pions is going to have one photon going in the forward direction and one going in the backward direction. So the question is, again, is the velocity of this photon going at the velocity of the pion plus the velocity of light, and the velocity of this at the pion minus the velocity of light? And the answer is no. Again, we can measure the velocity, and we see that the velocity of light is the same. So this is a huge verification of the postulates of Einstein. Okay, so let's now step into something else. Now we assume these two postulates, and we say they are right. So let's do a little clocking here. That's my way of doing a clock. We grab a flashlight, we grab a mirror. We can measure the distance between the flashlight and the mirror. And then we should have the flashlight emit a pulse. The pulse of light will go, bounce on the mirror, and come back to the flashlight. And we call that a cycle, a tick of the clock. And then the flashlight will emit another one, will go back and forth, and we will have a second tick, and so on. So this is a clock we do. And essentially we can say, well, we know what the velocity of light is. It's always the same in any reference frame anyway. And we can measure the distance. So we know that the time difference between clicks is just given by the distance over the velocity of light. So that's our clock. Now, we put this experiment, this flashlight and the mirror in hand, in one reference frame. And we have it move with respect to us. And then we look at that same clock that we just did. From the other reference frame, we will see this completely different. We will see this moving. So for all we know, we see the light doing this. We don't see the light going back and forth because the experiment is moving, and we see the light doing this. Now, the key question is that even in this reference frame, we have to say that the velocity of light in here is the same as it was in the other reference frame. Right? So then, if the distance that the light has to travel is larger than what we measured in that reference frame, when we were in this reference frame, we measured this distance. This distance, this path, is by necessity larger. But the velocity is the same. So to complete this peak in this reference frame, by necessity, it has to take a larger time, right? Because the path is larger. So that means that when we see one click in here, we see the click done in a larger time. So this means that for all we know, moving clocks, or anyone know in any reference frame, clocks that are moving run slower than non-moving clocks. It is, right? This is one click maybe once per second in this reference frame, but when you see it in here, it's happening 1.5 seconds. So you think, that clock is running slower, because it should have been a second and it's 1.5. And here I typically use beta. Beta is just the fractional velocity. It's something that goes between 0 and 1. So if you say beta equals 0.99, it's 99% velocity. And if you care about the questions that they derive, pay no attention to them if you don't care. I think this argument is easy enough, the path length, to realize of this. So this also means that if I'm walking at a velocity closer to the velocity of light, and of course you can't hear me, but you can read my lips, you would see my lips speaking very, very slow because of this problem. Of course, if you are speaking back to me, I would see you speaking very, very slow. It would be a very boring conversation. But this is very important. The time depends completely on the reference frame. Now let's talk a bit about space. We just talked about time. So we now know that time runs slower, or we see from one reference frame you see the time runs slower than another one. There's a very similar experiment you can do, and in this experiment you can put a flashlight in there and this time measure the distance based on the time, and use that the time between the two reference frames changes. And this is the way you would see that experiment go. You would see something like this. I don't know if the arrow is moving always with the same velocity over there, and when it's back, or I try to do so. And you can go through all the equations of this and actually show, because the time is different, then the length has to be different. That is, the length you measure in this reference frame and the one you measure in this one of the same object is different. So if I have this, and this measures a meter in here, now I throw it at very high velocity, you would not see it a meter long. You would see it maybe less, depending on the velocity, but never more. The maximum length you can measure of an object is measured on the rest frame. Any other frame that's moved with respect to this one will see this short. So that's another interesting thing, that moving lengths look shorter. And now we can combine this with the time. And so if I'm walking now at a velocity closer to the light, not only you see me speaking slower, but you also see me flatten as a pancake. So all the things that move, you will see very, very narrow in the direction of the moon. My height would be the same if I move in that direction, but my thickness would be smaller. So these are the Galilean transformations we were talking about that turn out to be wrong. And these are the new transformations. You should not pay too attention to it, except for the fact that now the distance and time are treated in a very symmetric way. You see, it's not like this, that the transformation of the time is completely different at the distance. Notice how well interconnected these two are. And these are the only transformations that work, and they allow the wave, the electric wave, the light, to be the same in your reference frame. And from this thing, you can infer the length contraction, which essentially depends on the velocity between the two frames. You can also get the time dilation and the addition of velocities. These are all things you can go through if you care. But one thing that's maybe important is that if this is the velocity between the two frames, right, 0.6 means 60% velocity of light, the factor that things look contracted or time dilated depends on that velocity. For example, if you are at 0.92, I believe, you get a factor of gamma of 2. That means if you're moving at 95% velocity of light, you see the length contraction by a factor of 2 and the time dilation by a factor of 2. Okay, time dilation. Is this real at all? So again, muons are particles that decay on average every 2 microseconds. They decay to 3 things. Right? How do we see this particle decay? This is the particle at rest. And then I'm going to put a counter in here. The counter is going to count time. So starts counting 1 microsecond, 2 microseconds, and the muon decays into these 3 particles, 1, 2, 3. Right? Nothing new in there. So notice that at 2 microseconds this blows up. Now you have the same particle moving closer to the velocity of light. And you see the particle moving that way, and this is the x-axis. And again, you expect, if the particle is moving at 98% the velocity of light, and decays in 2 microseconds, you expect to traverse 2 kilometers. So you expect this guy to come in here and to blow up in here. And it doesn't happen. And what happens is, because the velocity is so high, the gamma factor is about 5. That means the time dilation is about 5. Instead of leaving 2 microseconds in our reference frame, we see the time as being 10 microseconds, because it's multiplied by a factor of 10. So at that point, you see this not decaying here, but decaying there at 10. And one thing I should have really draw is that if muons do not have really size, so really I'm cheating when I do this, but if they had size, how would you see this size? You would see it contracted, right? That's the way you see it. So let's use the same example again, muons. But now, real muons, actually, what happens is we have the universe filled with particles going very, very fast. Some of these particles hit the upper layers of the atmosphere, producing muons, and muons are producing after. So let's see how both things see, how we see it from the base of a mountain, a muon coming down, and how the muon sees coming down to the base of the mountain. So as you view this in the Earth reference frame, the landscape has its normal size. If the muon had size, you would see it flatten like a pancake, like it did there. And the muon clock, the way you see it, is running 5 times slower. Right? So instead of decaying, instead of traveling only 2 kilometers, it travels 10 before decaying. Now, how does the muon see that? In the reference frame of the muon, if we were coming down with the muon, you would see that the muon has its normal size, right? Something like that. The landscape now is moving, but the landscape, since it's moving, is flattened like a pancake, so you see something like that. And the muon clock in its own reference frame is going to run normally because it's its own reference frame. The bottom line is that the muon in this case will travel, for all the muon nodes, will travel 2 kilometers at the normal speed and the normal clock time, and it will decay at the base of the mountain. In this frame, you see the muon, you would see the muon traveling more with a delay clock. So it's still going to decay in the base of the mountain. And I think that's the most important thing. No matter how you see it, no matter what frame you stand on, you can even be on a third frame, you're always going to predict the same thing. The muons will be decaying at the base of the mountain. So this time dilation, this length contraction, it doesn't matter. This is all a point of view from one reference frame. The results you get are always going to be the same. Okay, this is a very hard thing to do. I will just tell you the basic of this. This is another experiment that says how mass changes depending on the reference frame. So imagine you have 2 balls that bounce against each other, and they bounce perfectly symmetrically, something like that. And imagine now you go in one frame that moves with this ball. It moves in this component, not really with the ball, because the ball goes also down, but it moves like that, in this direction. In that reference frame, you will see this ball just going down and back, bouncing against a ball that goes like that. And of course, the same is true if you go to this reference frame, a reference frame that moves like this. You will see something like that in the reference frame. And now, you can just use conservation of momentum in this place, and that is going to tell you that the mass, in principle, the masses in here are the same, and have this system and this collision happen with 2 equal masses. But the mass in here does not necessarily have to be the same. So the mass of the 0 particle and the mass of the 1 particle is 2 in here. And if you use other equations, you actually see that the ratio between the masses depends on the velocity between 2 frames. That's telling you now also that not only time, not only length, also masses depend on the reference frame. And they depend also based on this gamma factor. If you measure some mass in here, and there's something moving over there with some velocity, they will measure a different mass. Now, I was very hard trying to get an easy way to derive E equals mc squared. No kind of. It's actually, the general relativity, all these things are easy to derive in the first years of college. General relativity, on the other hand, is very hard to derive. Mathematically, it's very complex. It turns out to explain this with the least amount of equations, it's even easier to explain general relativity than it is to explain this relativity. So, let me just give you this is what we found before, that the masses depend on gamma. And gamma is essentially this, is related to the velocity between the two frames. And this is an approximation you can do. You can actually do this with your calculator. Right? This number over here, do the calculation, and you will see that for a beta very close to 0, it's about this number you put in here. If you do it with a calculation, you see you get the same numbers. And you can put that in here and through a lot of equations. What you get at the very end is that this, the mass of the particle, as you see, times the c squared is the energy. It's essentially the rest energy, the energy you measure of the mass in here, with respect to the kinetic energy, which is Einstein's equation. I realize this is not easy to grasp from these things. But let me tell you one thing about that result, though. This is valid for everything. Right? The mass is larger, the larger the energy, and the energy mass equivalent. So if I have a spring and I compress it, it's going to be harder to push that spring. The inertial of this compressed spring is going to be larger than it is if it's not compressed. The same for a capacitor. I need some force to push a capacitor that's empty, but I need more force to push the capacitor as the capacitor is charged, because it has more energy. That applies all across the board. The more the energy, the more its mass is. Right, so let's switch topics completely. That was the basic of special relativity. And let's talk a bit about simultaneity. Let's talk about what is an event in relativity. An event is something that happens at a specific place and time. For example, this is an event that happens at some time, like that, in some position, or a postponement. And this is something else that happens at another position and another time. It doesn't have to be related at all, it's just two events. And from a reference frame that's moving with respect to this reference frame, you can use the equations before, and in fact you will see by using the Lorentz equation, the Lorentz transformation, that this is what you get. This is the difference in length you measure from this reference frame, and this is the difference in time between these two events that you measure in that reference frame. So now, assume these two events are simultaneous in this reference frame. Right? It's simultaneous, happen at the same time. Two lights going on. The question is, does a person in this reference frame see this as simultaneous? No. Why not? Because they are a different distance away. These two events are not seen as simultaneous. In fact, if that reference frame is moving in that direction, you see that a person in that reference frame is seeing this one happening first and this one happening later. Of course, if it were to go the other way around, you will see this happening first and that happening later. So the event in the direction of the moving reference frame happened first, because this guy sees the light coming from that one first. And let me ask you something. If these two events are simultaneous, can these two events be related? Can one of them be the cause of each other? Why not?
Because, well, there has to be something that would change the causality.
They have to be something that what?
I'm trying to. There would have to be something that would cause. They can't be the cause of something.
Well, so if these two things are simultaneous, but you see them here as non-simultaneous, right? So in this reference frame, they may have causality.
Right. I thought it was mutual causality doesn't exist. I think.
So that's exactly right. So it might be these two events because they happen simultaneous in one reference frame. There's one reference frame in which these two events are simultaneous. And there's no signal that can cover this distance in that reference frame, generating the causality. Right? If I have a bullet and I shoot a base, the bullet will go off my gun and hit the base. That would be E1 and E2. But it has to travel. It has to spend some time traveling. And if these are simultaneous, there's no way, there's no causality that can be done on that. Now, this is sort of tricky because then I say, but there's a frame in which this is not the case. There's a frame in which these two are not simultaneous. So in principle, there could be a signal that translates from one point to another. But the answer is also no. The special relativity is so well constructed that if it is simultaneous in if there is one reference frame in which it is simultaneous, you can guarantee that there's not going to be another one in which they are causally related. Okay, so let's talk about a few paradoxes, like the typical paradox of a car in the garage. Imagine you have a car like this one, and the car fits perfectly in the garage. That means you can close both doors very quickly, and the car is in there, no problem. No doors are open. So you move the car back some distance, and then you say, well, what happens if the car and the garage are moving close to each other? The car is in there, and now we give it some velocity. Well, let's see. The guy in the garage, the guy that's standing here, he says, well, the car looks shorter because it's moving. So no problem, the car will fit in. And let's say we time the doors such that when the front of the car is in here, both doors close. Right? So from the guy in the garage perspective, everything is fine, no problem there. Now the car driver is a little worried because he sees the garage looks much shorter. And he knows we're going to close both doors at the moment his front is in here. So there's a problem in here. So who's right? The guy in the garage or the guy of the driver? You want to guess? Okay. So let's see. This is tricky because technically both sentences are right. The car will fit in the garage and will not fit in the garage. What is the definition of fit? This fits. Certainly this does. This does not. And what's the difference between these three cases?
It's movement speed and point of reference.
Say that again?
It's movement speed and point of reference.
What's the difference in here for the definition of fit is that in this case we have the doors closed. In this case, no. Right? You don't say that this fits because essentially you couldn't put the car with both doors closed. You say this fits because you could. Right? So in the definition of fit, it's implicit the idea of simultaneity. It's implicit the idea of both doors closed. The car fits in the garage. We say that the car fits in the garage is if it is within the doors when both doors have been closed simultaneously. So fit requires the concept of simultaneity. And simultaneity, as we just saw, is a frame-dependent concept. So the fit that was mentioned by the driver is a different fit than that one mentioned by the guy in the garage. So with that in mind, let's see how both of them sees this event happening. So we do the same thing. What happens in this case? The guy is moving. At this point, we close the doors very fast, and he keeps on moving. Right? Imagine it takes nothing to close the door and open it. So in this case, it worked fine. Right? Both doors close simultaneously because the simultaneous was defined in this reference frame, not in the other one. How's that the driver see the closing of the door? Now, we are now in the driver position, right? The reference frame is now in the driver's position. So don't expect the car to go over there, expect the garage to come here. So the garage is coming. At that point, this door is closed. And then the other door actually closes much later. So the car still passes through. Go ahead. Okay, but that's fine. So let's talk at last about the twin paradox, which you probably know very well. And it's not a particular twin paradox I like very much, to be honest. But anyway, it is. So you have two twins, Earl and Anna. Numbers, the names are properly chosen because Earl stays on Earth and Anna travels to Andromeda. So this is Earth on Earth, and Anna is over there. And Andromeda is about 2 million light years away, far, far away. So Anna essentially reaches, Anna travels to Andromeda and comes back. Now she's traveling in a very specific way with a constant acceleration about the same we have right now, 1g. So her spaceship is constantly accelerating. And the way we see it, the way Earth sees it, is because she's moving, she sees her clock going slower and slower. And of course, the more she accelerates, the more Earth sees her time going slower and slower. So she eventually reaches Andromeda, and because she's going so fast, she can reach Andromeda. It doesn't matter, it's 2 million light years. Her time is passing so slow that she could outlive Earth and actually reach Andromeda. Check out the beaches and come back. And then Anna reaches the Earth 80 years older than she left. So Anna went in here when she was born and came back 80 years older. But that time Earth died 4 million years ago. That's the twin path. This is the explanation of what happens if you were actually able to do it. Now, people say, oh, this is a paradox. And you say, why? Because if the movement is relative, you can always say that Anna is staying and Earth is moving. So the movement is relative. So then, in that case, you would expect Anna to be dead and Earth to be alive. How can one be older than the other one? And the solution is simply that you cannot interpret Molly. Sorry, that was supposed to be Anna. That's an old slide. You cannot interpret Molly because Molly was moving. So you cannot interpret Molly, Anna at rest, and her moving away and back, simply because you can't determine which is the one that went away. The movement is not really fully symmetric between the two, because Anna had to accelerate to come back. You know, I said that she was accelerating all the way back. That's fine, but even if she weren't, if she wasn't with a constant uniform velocity all the way back, at the moment she needs to turn back, she has to accelerate, and that changes everything. Because when she accelerates, she can feel something. Earth, on the other hand, feels nothing. It's on Earth. So this is what we call the twin paradox or pseudo paradox, because it's not really a conflict of logics. One of the logics is actually wrong. And in fact, we have done this experiment in a very different way. We have put in one airport, we put 3 atomic clocks in a plane, and one staying in the airport, and then the 2 planes go all the way around the Earth and came back. And the time measurement of this atomic clock changed exactly by what was predicted by relativity. Now that's a hard experiment. It's not as simple as I put it in here because there's gravitational issues that we need to discuss as well. But that's all going to be part of the next part after the break.